Hello, IB Math Core Year students. Welcome back to Unit 8. Today we're talking about problem solving with trigonometry, and our EQ is how can I determine which triangle rules to use to solve a triangle problem? I know you guys all have triangle problems every day. I know I do. But when you do have problems involving triangles, whether they exist in a pure math sense or an applied real-world scenario, you can likely use trigonometry to find one of the measurements that you do need. Now, we have already learned several strategies, so how do you know which one to use? You need to ask yourself the following questions when trying to decide which path to take. So, the first thing I like to look at is it a right triangle? If so, then I'm going to go ahead and use good old Pythagorean Theorem, which says that the hypotenuse squared is going to indeed be equal to one leg squared plus another leg squared. Now, again, you know this as a squared plus b squared equals c squared, but you just want to make sure you remember that the one that's isolated on the other side of the equal sign is your hypotenuse. And then you can also use your SOHCAHTOA Trig Rules, where you know that your sine is equal to your opposite over hypotenuse side. Cosine of your given angle is going to be equal to the adjacent over the hypotenuse side. And then tangent of your given angle is going to be equal to your opposite over your adjacent side. So just pick the one that corresponds to the scenario that you have and you're good to go. If not, however, if you don't have a right triangle, then you're not going to be able to use these rules, so we have to use the things we've learned out in the past couple of lessons. The first thing that you can look for is the triangle an ASA or an SSA, meaning two angles with an included side, or is it two sides and then an angle? And if so, you can use the sine rule. Now, hopefully you can remember that the sine rule is going to be set up to where you have the sine of one of its angles over its corresponding side pair is going to be equal to another ratio of the sine of an angle over its corresponding pair. Now, it doesn't matter which pair that you use, so you just have to pick which ones are your corresponding side and angle pairs to work with. And again, the other thing that I would say is this is what you want to use if you're trying to find an angle, but if you need to find a side, then just use the reciprocal of this relationship. So we have A over sine of A, B over sine of B, or C over sine of C. And again, you're just looking for those corresponding side and angle pairs. This is the layout you want to use if you need to find a side. Now, note that there are some instances with side-side angle triangles that the cosine rule really should be used. This is called the ambiguous case. Unfortunately, we are not going to be discussing those in this course. You're only going to be dealing with cases where ASA or SSA triangles will indeed work for your situation. Now, if you don't have one of those scenarios where it's SSA or ASA, then maybe you have a situation where you have a side-side-side triangle or an SAS triangle where you have two sides plus an included angle, the angle that is formed by those two sides. And if that's the case, then you can go ahead and use the cosine rule, which I always build it in this case where I have one of the sides and its corresponding angle on the opposite side of the relationship. So we have a squared and then cosine a, those are on the outside. On the inside, we have the Pythagorean theorem, the rest of the Pythagorean theorem, b squared plus c squared, and then we have minus 2bc. So it's the remaining two sides make up the inside, and that makes it a lot easier for me to build this relationship, and I use it as appropriate. What you want to also remember here is that these guys, again, are going to be your corresponding side and angle pairs. Now, the other thing you want to think about, again, we mentioned this before, but we have here, B, B, C, C. All of these are going to also be corresponding side and angle pairs. So these are just things that you want to make sure you're paying attention to. What are my opposing side and angle pairs? So that way they can see that they correspond. And that's usually the next question that I'm asking myself is what are my corresponding side and angle pairs? Because this is how I build either one of these formulas. So identify which angles are opposite of which sides, because knowing these pairs is going to help you set up either your sine rule or your cosine rule. And then finally, what you want to be able to do is recognize, okay, well, what am I needing in the problem? Do I need one of the sides? Do I need one of the angles? Or maybe I need the area. Now, what you need in order to use one of our area formulas is you need two sides and an included angle of your triangle. Okay, if your triangle is not a right triangle in that case. Otherwise, maybe you can find the height and you can use our good old formula. The 1/2 base times height is going to be the area of any triangle, but a lot of times that's not going to work. So what we have to use instead is this other formula, and we're not going to derive it again, but here's another way that you can do this. The area of a triangle is going to be 1/2 AB sine of angle C. So what's important here with this formula again is that C, this is going to be the angle between two given sides. And this is going to be effectively another way that you can work with your 1/2 base times height. It's kind of a workaround if you don't know what that height of the triangle is, but if you have two sides with the included angle in between them, then you're going to be good to go to be able to find the area of any triangle. All right, let's put it into practice and actually look at some examples. All right, so let's take a look at this first example. The angles of elevation to the top of a mountain are measured from two different beacons at sea. We see that they are 29.7 degrees and 41.2 degrees, and that these two beacons are 1,473 meters apart. So I'm going to write that in here. So I've got some other kind of measurement now. And what I'm trying to find is how high is the mountain? What is this distance here? Well, I see quite a few different triangles to work with. I see first off this big right triangle here. I don't have either one of the sides to work with. I know one of the angles, but I don't have one of the complete sides to work with. So that's kind of out right now. Then there's also this right triangle that maybe I can work with if I do happen to know either one of these two sides. But again, I'm not sure how I'm going to find this. If I know that, then I would also know this side, and I would be able to use trigonometry, just standard SOHCAHTOA stuff either way. But I don't know those things. But here's what I do see also. I do see this other triangle right here that I could possibly be working with. And why that's important is because the two red and blue triangles then do share a side. Let's call this side X. And if they share that side, then that's going to help me maybe find a way to work with that blue right triangle. Okay, so I'm going to redraw this and see if I can't find a way to find that X side, this long side here from that second and closer beacon. I know this measurement here is 29.7 degrees. I know this measurement down here is 1,473 meters. And since this is 41.2 degrees, I know that's going to be a supplementary angle here. I'm just kind of like filling in all of the pieces that I know that I can kind of work with to answer this question. So let's find that bottom angle, because that's going to probably help us out. So we take 180, we subtract 41.2 from it. That's going to give us 138.8 degrees. And then, by the triangle sum theorem, I should also be able to know what this top angle is here. I want to get as much information about these as I can. So even though it's not ultimately, or it's not serving my purpose immediately, it might do so in just a little bit. So let's go ahead and take 180 to take away the two angles that we have on the inside, and we can see that that's going to be an 11.5 degree angle there. Now, why is this important? Let's go ahead and see, can we find some appropriate side and angle pairs? Well, here's one side with its corresponding angle. I can draw a line through the triangle to find those. The other one that I have, and this is why it's super important, because remember, what we wanted to find was this side right here. And I do now know what the corresponding side and angle is with that. We'll call that X, and that corresponds with this one here. So now I can set up law of sines to find that side X. If we can find side X, then we can find side H. So let's get to it. We'll set this up where I want to find the thing X, and that is over the corresponding side of that angle, 29.7 degrees. And I set it equal to, if I had a side on top on one side, I have to have the side on top of the other. So that was the side of 1,473. Divide that by sine of 11.5 degrees. I'm going to do a little bit of algebra here, rearranging, and then we'll punch into our calculator. So right from there, I can see that side x, while it's not the thing that I want, it does at least give me a good, useful measurement. I'm going to again write down a bunch of decimals here that I want to use because we don't want to run into intermediate rounding problems. So now we've got this. We know what side x is. If we know what side x is, let's look at this other triangle that we had in blue originally. Now we can see that we should be able to use just standard right triangle trig in order to answer this question. Because here we got 41.2 degrees. We know that this side is 3,660.6218 meters. And then we want to find side h. Side h, that's our opposite side. And then 3,660, that's our hypotenuse. So opposite and hypotenuse means we can work with sine in just general trigonometry. So we have sine of 41.2 degrees will equal our opposite side, h over 3,660.6218. Again, we're just going to do some rearranging now to get h by itself, and we will see that that's going to be the following calculation. Go over to our Desmos and punch it in. And we should get a measurement of 2,411.212, ... and that's going to be approximate for h, which means if we go to 3 significant figures, that's going to be about 2,410 meters, all by just knowing 2 angles and 1 distance. All right, let's go ahead and take a look at another example. This next one I think is going to be a little bit more straightforward, but let's see what we need to do with it. Now, to get from P to R, a park ranger has to walk along a path to Q and then to R. Otherwise, you'd be walking through a lake. Can't walk through a lake. That's silly. Now, what is the distance in straight line from P to R? So this is what we want to find. Go ahead and mark up your space. This is what we want to find. We're going to call that X. Recognize what we have in this triangle. I have a side, and I have an angle, and I have a side. Not only that, the angle is included between these two sides, so that we would say is an SAS triangle. And in an SAS triangle, this is where we want to be able to use the law of cosines, or what we might call the cosine rule. And here's what we want to recognize. Again, mark your corresponding side and angle pairs that you have. These are the two, and this is really all I need, because I have the thing that I want to find. I'm going to isolate it. And I'm going to put on the opposite side of the equation cosine of 112 degrees. And then I'm just going to use Pythagorean Theorem with the other two sides that I have, 175 squared plus 63 squared, minus 2 times the sides. And that's an easy way for me to build it. Now I recognize, okay, well, the only thing I need to do left is just to punch all this in the calculator, take a square root, or I can do it all in one step in the calculator. It's totally up to you. It does not matter whichever way you do it, but we can even just, from this point, we can say that X is going to be approximately what? Let's go to our calculator and punch it in. And there we see very quickly, not too much work. X is going to be approximately 207.01, ... so about 207 meters if we are rounding that to 3 sig figs. Boom. Done and done. Pretty easy once you know which process you go through. Unfortunately, I can't do those things unless I know which questions to ask. But since I know which questions to ask, I know which rules to use, and I'm ready to go. All right, you got 2 more. You do examples. The first one that you have, example number 3, not going to be too tough. Number 4 will challenge you a little bit. Try to put it together. Lots of moving pieces. We will go ahead and take a look at these in class next time. See you then.